Hey guys, what's up? We're back with day 55. We're going to change gears a little bit. Nice job today working on connecting the fundamental theorem of calculus to those graphs, right? I saw some really good learning going on, really good connections made. Today we're looking at a way to solve more difficult integrals. We're specifically looking at indefinite integrals today. And it's a method called u-substitution. Now, with derivatives, we have lots of rules for derivatives. We can do the power rule, the product rule, the quotient rule, and the chain rule. Integration is a lot more difficult than that because we don't have a power rule for integrals. We don't have a product rule for integrals or a quotient rule or a chain rule. But what we have, one method for solving tough ones is called u-substitution. So when we take a look at u-substitution here, this is a way that we can, it's kind of integration's answer to the chain rule. So for review here really quick, let's just review the chain rule 1 second. So let's say that we have a function f of x, and we know that f of x equals sine of x cubed. Now, if I asked you to do the derivative of this, you would recognize, hey, I have a function x cubed within a function sine of x. This is a classic chain rule problem. So what would you do? Well, you'd say, I'm going to do the derivative of the outer function, right? Here's my inner. Here's my outer. I do the derivative of the outside with respect to the inside. And then I'd multiply by the derivative of the inside. The derivative of x cubed is 3x squared. Okay, and cleaning that up, I'd say my answer is 3x squared cosine of x cubed. Okay, so that's just your basic chain rule for derivatives. So what if I gave you this question? What if I asked you, what is the integral of 3x squared times cosine of x cubed dx? Well, again, I don't have a product rule for integration. So I can't just follow a formula and get my integral that way, okay? But when I look at this question, right, since I just asked you about the derivative of sine of x cubed, hopefully you can say, okay, so if f of x is sine of x cubed, f prime is 3x squared cosine of x cubed, that must mean the antiderivative of 3x squared cosine of x cubed, right? We can see, oh, if I do the integral of f prime, should give me this answer of f. Okay, but since it's an indefinite integral, there are infinitely many, I would just write plus c to account for that. The question is, how could I solve that indefinite integral if I didn't just do that derivative? Okay? So that's where u-substitution comes into play. Now, what we're going to look for on u-substitution, right, we're going to solve this very same integral that we just got, okay, but we're going to solve it without having done the derivative ahead of time. Okay? Now, u-substitution, I like to say, is integration's answer for the chain rule. Now, when we do the chain rule, right, the chain rule says if I do the derivative of f of g of x, I get f prime of g times g prime. So what I see coming up in all of these chain rules is I see a function g and I see a g prime. Right? I see a function and its derivative multiplied together with something else going around. So when I do these problems, I'm going to do what's called u-substitution. And I'm going to let u be like the g of x in that f prime of g of x times g prime of x. Okay? So when I see this problem, let's just start it from scratch. What you need to get really good at looking for is, do you see the g and the g prime? Do you see a function and something that looks like its derivative? Well, when I look here, what I see is an x cubed and a 3x squared. And I know 3x squared is the derivative of x cubed. Right? So I'm seeing this pattern. I see something, I see a function, and its derivative. It's like seeing the g and the g prime in f prime of g of x times g prime of x. So what I want to do is I want to choose not the derivative part, not the 3x squared part, but the other one. I want to choose x cubed to be my u. And I'm just going to let that be a substitution. So what I'm going to say here is I'm just going to let u equal x cubed. Okay. And as we do this more and more, you'll get better and better at choosing your u. Then what I'm going to do is do the derivative of u with respect to x. So instead of saying dy dx, we're going to say du dx. Well, du dx would have to be the derivative of x cubed. Well, that's 3x squared. And then the one kind of funky thing I do here is I just like to get it so it says du only. So I'm basically, in my head, I'm just going to multiply both sides by dx. Eventually, we'll just write du equals, but this is where it's coming from. And what I get is du equals 3x squared dx. And what I'm going to do is I'm going to substitute into this integral, this difficult looking integral that's in terms of x. I'm going to change it to an easier to do integral that's in terms of u. Okay? So that's the substitution that I'm going to do here. Okay? And when I rewrite this integral, I'm now going to write an integral entirely about u. And I actually start with my du. So I'm going to write my integral. I'm just going to put an equal sign here. And I'm going to write a new integral in terms of u. So I'm going to be integrating with respect to du. Now, plugging du into the integral, I have an equivalency here. Du is equal to 3x squared dx. Right down here. So putting that du into the integral substitutes out for the 3x squared and the dx. I like to kind of cross those things off to know that I have accounted for them. So du is equal to 3x squared dx. So I'm going to replace the 3x squared dx part of that integral. I can just replace it simply with du. Now notice that I never accounted for cosine. Cosine didn't show up in anything down there in my u or my du. So it has to stay cosine. That cosine has to be there. But that x cubed is going to be, I'm going to be able to substitute in x cubed. And I have that equivalency. It was the first one I wrote. X cubed is equal to u. So again, the cosine was never accounted for anything down there, so that just transfers over. the x cubed became the u, and the 3x squared dx became du. And what I did is I took a difficult integral, right, 3x squared times cosine of x cubed dx, and I changed it into an easy integral, cosine u du. Right, I'm thinking of this is just like the integral of cosine. Well, I know the integral of cosine is sine. So I just go ahead and do this integral. Now I'm doing everything in terms of u. The integral of cosine u du, that would equal sine of u plus c. And the last step I have to do, since my question was in terms of x, my answer should be in terms of x. So I'm going to make one last substitution here. I'm going to replace that u with that x cubed, that equivalency that I have here. I'm going to plug in x cubed for u, and I'm going to get an answer of sine of x cubed plus c. And when we look back up, that's what we knew the answer should be. It's kind of like magic, the substitution. Okay. Let's take a look at another example real quick. And this looks like a nasty, tough integral to do. The integral of 2x over x squared plus 5. Yikes. Okay. But what I see here, what I need you to start seeing is that, let's think about that x squared. What's the derivative of x squared? Well, the derivative of x squared is 2x. And notice that 2x shows up in there. Okay? But not only is x squared's derivative 2x, but the whole denominator, right, including that plus 5, x squared plus 5's derivative is 2x as well. So what I want to do is I want to choose the u to be as big as I can and still have a du show up. So what I'm going to do is I'm going to choose u to be x squared plus 5. That means du dx would be 2x. But again, I want you to get in the habit of, right, du over dx. I'm just going to multiply that dx to be over here and say du equals 2x dx. What I see is, okay, I have a u. My du also happens to be something that's in this integral. So this looks like something I can solve with u-substitution. Okay, and once again, I always start by making my substitution. I put the du in right away. Yeah, put the du at the back. That du is accounting for the 2x and the dx. So those are canceled out. But I still have a fraction here, and I still need a placeholder on top of that fraction. The placeholder is the coefficient that's not written, which is 1. What about this x squared plus 5? Well, I'm letting x squared plus 5 equal u. So I'm just going to put a u in the bottom, and that's going to account for that x squared plus 5. And as you can see, I've accounted for everything. Right? I don't have a floating cosine or sine or anything like that. And what I did is I took a difficult integral, 2x over x squared plus 5 dx, and changed it into an easy integral, 1 over u du. What is the integral of 1 over u? I still have to do my antiderivative here, but this is one I recognize as natural log. So my answer here would be natural log absolute value of u plus c. But again, I can't answer a question in terms of x with an answer in terms of u. So my last move is to sub back in for u. I'm going to go ahead and plug this back in. I get natural log absolute value x squared plus 5 plus c. Now, what about those absolute value bars? Well, I know that if I have a negative in there, it makes it positive. But think about the function x squared plus 5. Whenever I square a number, whether it's positive or negative, it's going to become 0 or higher. Plus 5 will always be a positive number. So in fact, I can write this with just parentheses rather than absolute value brackets. And I can call this now, if it would have said x squared minus 5, then that could be negative, and I'd have to leave the absolute value brackets. Okay. Let's take a look at another one. So here I have, oh, I forgot my dx. Hold on. Again, this is a nasty looking integral. But what I have here is the integral of x squared times the square root of x cubed plus 9 dx. Okay? But again, what I see is I see a function x cubed plus 9. Well, I know the derivative of x cubed plus 9 is 3x squared. Now, I really wish it said 3x squared out front, but it doesn't say 3x squared. Okay, but I can still do my u-substitution. We just have to make a little adjustment with our du. I'll show you what I mean. I'm going to let u equal that x cubed plus 9. I'm not going to include the square root here, because if I included the square root, the derivative would be a chain rule and it'd be much more difficult, and it wouldn't come out to be anything close to x squared. Right? It'd be half x cubed plus 9 to the negative half times 3x squared. Hideous. So I'm just going to leave the square root, just like I left the cos alone in example 1. So I'm going to let u equal x cubed plus 9. Du then is going to equal the derivative of x cubed plus 9 is 3x squared dx. Notice I'm just automatically moving that dx to the back. So what I need to do now is make an adjustment. Notice how it's x squared dx in the problem, but I have 3x squared dx here. So I just need to make an adjustment, and I can make that adjustment as long as it's just multiplying by a number, a coefficient. Right? So the question is, what number could I multiply 3x squared dx by to equal just x squared dx? Well, I would have to multiply by the number 1/3. So I'm just going to do that to both sides of this equation. 1/3 du equals 1/3 of 3x squared dx would just be, the 1/3 and the 3 would cancel to make 1x squared dx. So I call this making it match, right? I want to make my du match what's in the integral, and I can make it match by multiplying by 1/3 on both sides. Instead of thinking of dividing by 3, I would like you to think of multiplying by 1/3. Okay? Now, when I adjust my du like this, okay, I have an adjusted du now. When I go to write my new integral, any coefficient I have in front of my du, I'm just going to write out in front of the integral sign. I put my 1/3 in the front, and I put my du at the back. Because we know from integration rules, if we have a constant if we're integrating a constant times a function, we can always put that constant out front. I want you to just get in the habit of always doing that. Now that 1/3 du is accounting for the x squared and the dx. Okay? So here's what I have left. I have the square root, and I have x cubed plus 9. Well, x cubed plus 9 is going to be subbed in for u, but I never accounted for this square root, so it has to transfer over and be a square root in here. Now, this isn't the easiest integral, but it is certainly much easier than what it was before. I can integrate u to the 1/2 power. Right? Before I do my integral, I'm just going to write that out. 1/3 integral u to the 1/2, because square root means 1/2 power. Now I'm just going to bump and divide. I'm going to bump my power. I'm going to keep my 1/3. I'm going to bump my power up by 1 and divide by 3/2. Dividing by 3/2 is the same as multiplying by 2/3. The last thing I need to do here, I just want to combine these. 1/3 times 2/3 is 2/9. U to the 3/2 plus c. And again, I don't want my answer to be in terms of u, and the question was in terms of x. So what am I going to do? Well, I'm going to substitute this back in for the u. And I'm going to get 2/9 parenthesis x cubed plus 9. The 3/2 power plus. Now, you can always test your answer by doing the derivative of your answer. The derivative of my answer should go back to that original problem of x squared times the square root of x cubed plus 9. I'm just going to show you that quick here. Right, I can test by doing the derivative. So this is a chain rule. I have a function within a function. So I do the derivative of the outside. I'm going to multiply that out front. With respect to the inside, keep the inside the same and reduce the power by 1. But it's a chain rule, so I also have to multiply by the derivative of the inside. Now that doesn't look anything like what we started with. But as we start solving this out, we can see the 2's are going to cancel here. This 3 is going to become a 1. The 9 is going to become a 3, and I'm going to get 1/3. Okay. Square root of x cubed plus 9. Right? I just changed this 1/2 power up here back into a square root. Times 3x squared. And what I'm going to see is the 3 and the 1/3 are going to multiply together to make 1. Putting that x squared out front, I do get that exact same thing, right? This is exactly where I started with up here. Okay. So that's going to be it for today. We'll look at some of these u-substitution problems Monday in class. Right? They're kind of tricky, but the more we do it and the more we practice, the easier they become. All right, that's it for today. Have a great weekend. See you guys Monday. 2 chains. Bye.